Hi everyone, I am Ajay Kumar Mahato and today I am going to present my work bearing paper ID number 6089 on low voltage organic field effect transistors with room temperature deposited dielectric layer. These are the outline of my presentation. So let's start with a brief introduction. Organic electronics, it is a branch of electronics which deals with organic materials. Among various organic devices, organic field effect transistors, also known as organic transistors, are commonly preferred for device fabrication because of its several advantages, such as thin fabrication, lightweight, low temperature deposition, and low cost. These are couple of expectations from organic electronics in future, which includes high performance, low power consumption, implementation on flexible substrates, better operational stability, and feasibility on unconventional substrate like paper substrate and plastic substrate. The common problem that we are facing in fabricating OFET devices, it is its voltage of operation when we are using conventional dielectric like SiO2. Using conventional dielectric like SiO2, the operating voltage of OFETs are of the order of -30 volt to -50 volt, which is not acceptable in future flexible technologies. To overcome this problem, we could either improve the aspect ratio or the capacitance density of the gate dielectric layer. Improving the aspect ratio or increasing the aspect ratio of OFET devices is not a suitable option as it will increase the device area and hence it will reduce the device density. Thus, controlling the gate capacitance density could be considered as a better options. Gate capacitance density could be easily controlled by using suitable gate dielectric with higher values of dielectric constant. These are couple of high-K dielectric material which has been explored significantly over the past few years using various deposition schemes such as spin coating, sol gel method, pulse layer deposition, atomic layer deposition, sputtering, and so on. The common problem that we could observe in this table, it is the deposition temperature which is in the range of 200 degrees centigrade to 750 degrees centigrade, which is not acceptable in future flexible organic technology. In this study, we have deposited BST dielectric layer at various temperatures. The BST thin film deposition has done at various temperatures starting from room temperature to 100 degrees centigrade, then 200 degrees centigrade, 400 degrees centigrade, and 600 degrees centigrade. In XRD characterization, we could observe that the thin film BST layer which is deposited at room temperature, it is amorphous in nature, whereas the BST layer deposited at 600 degrees centigrade is crystalline in nature. Thus, room temperature deposition of BST layer which is amorphous in nature could be considered as a gate dielectric layer in OFET device fabrication. Secondly, we have analyzed the surface morphology or the surface roughness of BST layer depositing at different temperature, starting from room temperature to higher temperature. And in this AFM characterization, we could observe that the surface roughness of the BST layer increases with increase in the deposition temperature, and it is least for the BST layer which is deposited at room temperature. Thus, we could conclude that the BST layer deposited at room temperature, it is amorphous in nature with excellent smooth thin film characteristics, and hence it could be considered as an option for OFET device fabrication. Next, we have analyzed the gate capacitance density characteristics. So in these characteristics, we could observe that the gate capacitance density of the BST layer deposited at room temperature exhibited excellent stability over its capacitance density over a wide range of frequency range. In the current density plot, we could observe that the BST layer deposited at room temperature exhibited least value of leakage current compared to the other deposition conditions. Thus, room temperature deposition of BST dielectric layer is an good option for OFET device fabrication. This is the device structure which we have used for our OFET fabrication. FTO coated glass is used as a substrate, BST as a gate dielectric layer, and TIPS-Pentacene PS plant as an active semiconductor layer. And this is the optical image of our fabricated device. Next, we have analyzed its transfer and output characteristics. In transfer characteristics, we could observe that the TIPS-Pentacene devices were operated at -3 volt, which is remarkable when comparing with the OFET devices which were fabricated using SiO2 gate dielectric, where the operating voltage is of the order of -30 to -50 volt. It also represents that the replacement of gate dielectric with suitable material like BST could significantly reduce the operating voltage. The switching ratio we obtained, it was 10 to the power 4 with an average mobility of 0.6 plus or minus 0.07 centimeter square volt inverse second inverse. In the output characteristics plot, we could observe that the representative device exhibited good saturation behavior in its output characteristics. Next, we have analyzed the operational stability and we have performed the multiple scan as well as the electrical bias stress studies in it. In multiple scan, we have captured the transfer characteristics of the representative device over 100 cycle, and we found that the drain characteristics, it is stable over 100 number of cycles. This is the drive parameter plot of the representative device. Here we could observe that the device exhibited good stability over its drain current over multiple scan. Similarly, the threshold voltage of the representative device, it also exhibited stability over multiple scan. Next, in our electrical bias test characteristics, the electrical bias condition we have applied, it is VGS equals to VDS equals to -3 volt for a duration of 1 hour. And we observe that our device exhibited decay of 14% in its drain characteristics. And in shift in threshold voltage characteristics, we observe that the device exhibited 0.2 volt of shift in threshold voltage characteristics. Thus, we found that the device exhibited excellent stability in both multiple scan and electrical bias test condition. Next, we have analyzed inverter circuit with an external load resistance. In our previous slide, we found that the representative device exhibited drain current of the order of microampere, and hence to realize an inverter circuit, we have used load resistance of the order of mega ohm. Different load resistance 10 mega ohm, 20 mega ohm, 30 mega ohm, 40 mega ohm, and 50 mega ohm we have used to realize the inverter characteristics. And in the inverter transfer characteristics, we could observe that the inverter transfer characteristics improve with increase in the load resistance, and we found with 50 mega ohm load resistance, the inverter transfer characteristics, it is the best inverter transfer characteristics in our studies. Next, we have analyzed its dynamic characteristics over multiple cycles, and we found that the representative device exhibited good stability in its inverter dynamic characteristics over multiple cycles. So it's time for the conclusion. We would like to conclude that BST as a gate dielectric could be a better options for OFET device fabrication. The representative devices were operated at -3 volt with an switching ratio of 10 to the power 4 and average mobility of 0.6 plus or minus 0.07 centimeter square volt inverse second inverse with near zero threshold voltage. Devices exhibited excellent operational stability under both multiple scan and bi-stress condition, and the devices exhibited decent inverter transfer and dynamic characteristics with external load resistance. We would like to acknowledge Visvaria PhD scheme and DST for providing financial support. Thank you.